Alright, this is the review for the non-calculated part of the fall final exam for Calc AB. So if we look at number one, find the limit as n goes to 0 of that quotient. When we find limits, first thing we want to try to do is direct substitution if we can. So if we try to directly substitute a 0 for n, both the top and bottom, I get 0 over the square root of 9, which is 3 minus 3, which gives me 0 over 0, which is indeterminate form, so that means I have to do something else to get my solution. So what we're going to do is multiply both the numerator and the denominator by the conjugate, which is of the denominator, which is square root of n plus 9 plus 3, or the square root of n plus 9 plus 3. And so we're left with the limit as n goes to 0 of n times the square root of n plus 9 plus 3 over, and then the whole point of doing the conjugate is so that we have perfect squares, and it's a sum and a difference, so we can apply our multiplication rules for multiplying binomials, and that means I'm just going to square the first term. So it's the multiplication rules for multiplying conjugates, sorry. And that's going to allow me to just square the first term, which gives me n plus 9. And then I'm going to square the last term, or actually multiply the last term. Negative 3 times positive 3 is minus 9. And we can see right away that those 9s cancel out. So I'm left with the limit as n goes to 0 of n times the square root of n plus 9 plus 3 over n. And now the n's cancel out, and at this point now I have no reason to not directly substitute a 0 because that n on the bottom is gone. So I can directly substitute the square root of 0 plus 9 plus 3, which is the square root of 9, which is 3 plus 3, which gives me a limit of 6. Number 2, same thing, I'm going to try to plug in a 4, but this time plugging in a 4 is going to give me a 0 on the bottom. Again, that's going to be bad, so I'm going to have to find something else to do. We could multiply by the conjugate of the denominator, but that's not going to help us. So instead, we're going to multiply again by the conjugate of the numerator. So this can be the square root of x plus 12 plus 4 over the square root of x plus 12 plus 4. And we're left with the limit as x goes to 4. Once again, I'm going to follow my rules for multiplying conjugates. I get radical x plus 12 times radical x plus 12, which is just x plus 12, minus 16 over x minus 4 times radical x plus 12 plus 4. And now we can go ahead and move to the next step. The limit as x goes to 4, we're going to start to reduce this. 12 take away 16 is x minus 4 over x minus 4 times square root of x plus 12 plus 4. And now we can see that we have a factor of x minus 4 on the top, that same factor on the bottom. Those cancel out. I get the limit as x goes to 4 of 1 over radical x plus 12 plus 4. And now we can directly substitute. And we get 1 over square root of 4 plus 12 is the square root of 16, which is 4, plus the other 4 that we already had, gives me 1/8. Number 3, use the graph of f of x to find each limit. So the first two, we find the limit as x goes to -1. So we find -1, which is right here, which looks like our vertical asymptote. Since the left bound, and the right bound behavior are different. Remember, there were three ways that we did not have a limit. The bounds were different. The bounds went to infinity, or the function oscillates. So in this case, since the bounds are different and they also go to both negative and positive infinity, we can say that the limit does not exist. For part 2, find the limit as x approaches -1 from the plus side. So that means the right side of -1. So we're going to move in starting as far right as we can go, and we're approaching that asymptote. And as we do that, we start going up. We increase to infinity, so our function is, or the limit of our function is infinity at -1 from the right. And then we approach -1 from the left, same idea, but now this time I'm as far left as I can go, and I start approaching that asymptote, and we're left with that it's approaching -infinity. Part 4 now, find the limit as x goes to 0 of f of x. So as x goes to 0, so here's 0, that's x equals 0, and my graph, both the left and the right side of my graph approach the same value, which it appears to be approaching +1. And then finally, part 5, find the limit of f of x as x goes to -infinity. Well, that means I'm looking at as far left on my graph as I possibly can go. As my graph moves all the way to the left, I'm looking way out here, and my graph is approaching 0. Number 4. Find the limit as delta x goes to 0 of the function cosine of 3 pi over 2 plus delta x minus 0 over delta x. And when I look at this, I see that that almost looks like the difference quotient. The only exception is right here, where that says minus 0, we would like it to say, if it was truly the difference quotient, this would be the cosine of 3 pi over 2. Well, if we think about it just for a second, what is the cosine of 3 pi over 2? Well, 3 pi over 2 is right here on our unit circle, and that ordered pair is 0, -1. Cosine is my x value, so really that minus 0 is the cosine of 3 pi over 2. So what I truly have is the limit as delta x goes to 0 of the cosine of 3 pi over 2 plus delta x minus the cosine of 3 pi over 2 all over delta x. And we know that that difference quotient is the same as the derivative of our function. And specifically, it's going to be the derivative of our function at 3 pi over 2. So what's our function that we're dealing with? Our parent function that we're starting with is the cosine of x, and we are looking for the derivative at 3 pi over 2, which means we're looking for the derivative of cosine of x. The derivative of cosine of x is negative sine of x. So when we evaluate that, I have the derivative at 3 pi over 2, which is negative sine of 3 pi over 2. And then if I go back to the unit circle, here's 3 pi over 2 once again. That's sine. So I have -1, which gives me a limit of 1. 5. Same kind of idea. That almost looks like the difference quotient, but once again we have that. Well, if we want that to be the difference quotient, it would have to be the tangent of pi fourths. Once again, if we think about the unit circle for a second, pi fourths is right here. That ordered pair is rad 2 over 2, rad 2 over 2. And then the tangent is the ratio of sine over cosine. So it's really rad 2 over 2 over rad 2 over 2, which is 1. So once again, even though it doesn't look like it right away, if we think for just a second, that means the limit as h goes to 0 of tan of pi fourths plus h minus the tangent of pi fourths all over h. So once again, my function that we're dealing with, f of x, is just the tangent of x, and we are looking for f prime of pi fourths is what we're trying to evaluate. So f prime of x is equal to secant squared x, which means the f prime of pi fourths is going to be secant squared of pi fourths. Well, secant squared is, it's going to be the reciprocal of cosine squared. Well, cosine is rad 2 over 2. So I have 1 over rad 2 over 2. That whole thing is squared. So we end up with 1 over 2 over 4, which is, if we flip that around, actually I'm going to go back one step. We could do it this way, but just realized I probably just confused some of you. So let's fix that. So secant squared is the reciprocal of cosine, or secant is the reciprocal of cosine. So it's going to be the reciprocal of rad 2 over 2, so that's 2 over rad 2. Now we're going to square it. That looks a little bit better. And when we square it, we get 4 over 2, which is just 2. All right, moving on to number 6. That is, once again, that is for sure a difference quotient. We are evaluating the derivative of some function g at 2, and that has a derivative of -1. So what does that tell us? Well, it tells us that the derivative of g at 2 is -1. That's 2. It also tells us, since it has a derivative, since it's differentiable at 2, it's also continuous at 2, because differentiability implies continuity. And what else do we know? Well, we know that the derivative is -1. So if the derivative is -1, if we apply our first derivative test, that means that our function g is decreasing at the x value, which that x value, once again, is at 2. So g is decreasing at 2. So our answers are 2, 3, and 5. Number 7. This one almost looks like the difference quotient once again, but it's not quite because I don't have the x plus h in here. But this for sure, right there, is the slope of a secant line. And if we're valuing the limit at 4 for the slope of a secant line, that is essentially the same as the derivative of a function at a point, specifically the point x equals 4. So what's true? Well, once again, f prime of 4 is going to be 2, or f prime of 4 is 0, which is option 2. Once again, if it has a derivative, which means it's differentiable, then it is also automatically continuous. So 3 also applies. And finally, since the derivative is 0, we know that when the derivative is 0, that means that it is a critical number. We do not yet know if it's a relative max or not, though. It is not a point of inflection because that would have to be the second derivative. All right, so number 8 says use the graph below to answer the following. So we're going to use this graph right here. List the values with a removable discontinuity. So a removable discontinuity is one where we can move the discontinuity and we would have a continuous function at that point. So that would be places where there's just a hole rather than a jump or an asymptote. So if we look at this, we have a removable discontinuity at x equals -4, because at -4, if I can fill that hole, I can choose to redefine this point up here, and then it fills the hole, and now it's a continuous graph, and there's no other weird things going on. At -2, that's a non-removable discontinuity because there's a vertical asymptote. At 0, there's a non-removable discontinuity because it's a jump. And then at +5, that's another discontinuity, but that is once again removable. So -4 and 5 are removable, and it's removable because we could define a new point that exists where we're missing a value. And then part 2 lists the x values with a non-removable discontinuity. That's going to be at x equals -2. And pause and 0. At -2 we have an asymptote. That's not removable. And at 0 we have this jump, so that's also non-removable. Part 3, for what values of a, does the limit x equal a of f of x not exist? So we're looking for where is there not a limit to the function? Well, there's not going to be a limit at any place where the left and the right behavior of the graph don't converge on the same point. That's going to happen at vertical asymptotes, jumps, and oscillations. So if we're looking at the graph, that's going to be at x equals -2 and at 0, or two places where the limit does not exist. Now, we talked about in class that sometimes kinks, like this kink down here, are also where the limit does not exist, but in this case, because the left side is a curve approaching that value, and then the right side is a line, they still have a limit because they're both approaching the same value. It's just when we have an absolute value function and we look at the two sides, the left side always has a slope of -1 or negative some number, and the right side always has a slope of positive some number if it's absolute value. And then for 4, for what values of b do the limit as x approaches b of f of x and f of b exist? So the limit exists and b exists, but the limit does not equal the value of the function. Well, that's going to be any place where we have the graph is approaching a value, but b, the function is defined at a different value, and that's only going to happen at -4, and that's because the limit approaches 2, but the value of the function is 0. And then let's go on to number 9. Find the derivative of f if f is defined as x cubed plus 2x squared plus 4 all over x squared. I'm going to show you guys two ways to do this. So the first way is to use the quotient rule. We know that the quotient rule is defined as the derivative of the top, which is 3x squared plus 4x times the bottom minus the top times the derivative of the bottom all over the bottom squared. So we get that, and now we're going to go ahead and simplify. So if we distribute the x squared, we get 3x to the 4th plus 4x cubed. I'm going to distribute the negative at the same time that I'm multiplying by the 2x. So I've got -2x to the 4th minus 4x cubed minus 8x all over x to the 4th. So f prime of x is equal to, let's see, 3x to the 4th minus 2x to the 4th. That leaves me with x to the 4th. The 4x cubes cancel, so I've got minus 8x all over x to the 4th. And now I can simplify by dividing everything by an x. I can divide everything by an x. And I've got x cubed minus 8 over x cubed. So that's one method for finding the derivative. The second method is, since I have a single denominator, I can go ahead and divide everything by that denominator right away. So I can define f as being x cubed divided by x squared, which is just x, and then 2x squared divided by x squared. So first I did x cubed divided by x squared, that gives me x. Then I did 2x squared divided by x squared, that's just going to be plus 2. And then 4 divided by x squared is going to be 4 over x squared. And now I just have a polynomial-like function. And now if I take the derivative, well, the derivative of x is 1, plus the constant 2 goes away, and then 4 over x squared, I can treat that as 4x to the negative second. So I get minus 8x to the negative third, and that just becomes 1 plus 8 over x cubed, which this is equivalent to that because I can simplify the first derivative that I did. I can divide everything by x cubed, and I really just get 1 minus 8 over x cubed. So those are equivalent. They're just two different ways to approach it in case we don't want to use the difference quotient, or not the difference quotient, the quotient rule for derivatives. Number 10, given that y is equal to cosine squared of 5 minus x squared, find dy dx. Well, I'm going to have to use the chain rule to do this. First thing we need to remember is that even though it says cosine squared of 5 minus x squared, we are going to treat it like it's the cosine of 5 minus x squared all squared. That's the way we're going to do it. And now we can use the power rule, and we're going to use the chain rule twice. We're going to start with y prime is equal to 2, and I'm going to use different colors so we can see what's going on here. Cosine 5 minus x squared, and now I'm to the first power, so I took the derivative of the outside, times, now I move inside one step, so that's going to be the derivative of the cosine of 5x squared. Well, the derivative of cosine is negative sine of 5 minus x squared. And then I have to take one more derivative, and that is the derivative of the inside of that function. So I'm going to multiply that by negative 2x. So that's my derivative. Now I just have to simplify it. Y prime is equal to 2 times negative 2x times this negative here. So I get positive 4x. And then I have times the cosine of 5 minus x squared times sine of 5 minus x squared. And that is my derivative after I apply the chain rule twice. Moving on. So for 11, g of x is equal to sine cubed of 2x. Again, we're going to treat that like it's the sine of 2x all to the third power. So once again, we're going to have to apply the chain rule multiple times. Since we're taking the second derivative, we're going to start by finding the first derivative. So we've got 3 times the sine of 2x all squared times the derivative of the sine of 2x, which is cosine of 2x, times the derivative of 2x, which is just 2, and that's going to leave me with 6 sine squared of 2x times the cosine of 2x. That's my first derivative. And now I'm going to take the second derivative, and I'm going to have to apply the product rule. I have the f function, and here's the g function. So the second derivative, I'm going to take the derivative of 6 sine squared of 2x. Once again, sine squared, I'm going to treat that like that 2 comes out front. So I've got 12 sine of 2x times the derivative of sine, which is cosine 2x times that 2 for the derivative of 2x times the cosine of 2x. And then I'm going to add that to 6 sine squared of 2x times, I'm going to take the derivative of cosine of 2x, which is negative sine of 2x times that 2 for its chain rule. And so when I simplify this, I get 24. So I'm looking at all this right now. 24 cosine squared 2x sine 2x plus negative 12 sine cubed of 2x. And now we'll notice that when we look at these two terms, we have a 12 in common, and we also have a sine of 2x in common, and then we're going to be left with, so when I pull out a 12, I'm left with a 2 cosine squared of 2x. The sine 2x is taken out, minus, so when I pulled out the 12, I'm left with a negative 1, and I'm left with a sine squared of 2x. And so now I compare, and it looks like 12 sine of 2x times 2 cosine squared of 2x minus sine squared of 2x is going to be my final answer, D. Alright, then number 12. The derivative of f is defined as x cubed times x plus 1 squared times x minus 4. Which of the following statements must the function f have? So if that's the derivative, we know that one of the first things we do with the derivative is if set equal to 0. So 0 is equal to x cubed times x plus 1 squared times x minus 4, which tells me that x equals 0, negative 1, and positive 4. Those are going to be my critical values. So what do critical values tell us? Well, they tell us that we have maxes or mins at any of those values. So we need to figure out which one's a max and which one's a min. So if we make a chart, we have negative 1, 0, and positive 4, and we're going to pick values outside of each of those intervals. I'm going to pick a negative 2, a 1/2, and I'm going to pick 1 and 5 and see what's going on each of those sides. So we're going to plug in, we're applying the first derivative test, so I'm going to take these values in between the intervals and I'm going to plug them into my derivative. So negative 2 cubed, remember we don't really, since everything's being multiplied, we don't really care what the number is, we just care about what the sign is going to be. So negative 2 cubed is going to stay negative. Negative 2 plus 1, well, no matter what that is, it's squared, so that's going to become positive. And then negative 2 minus 4 is negative 6, so that's negative again. Negative, positive, negative leaves me with a negative value. The 1/2 cubed is positive. 1/2 plus 1 squared is still positive. And 1/2 minus 4, that's going to be negative, so I get negative here. Negative times a positive times a negative for this first one is a positive, not a negative. Sorry about that. Now I check positive 1. 1 cubed is positive. 1 plus 1 squared is positive. And 1 minus 4 is negative. So you get a negative value there. And I just realized that I used a positive 1/2 and I should have used a negative 1/2 in that interval because I'm looking between negative 1 and 0. So let's fix that real quick. So now if I plug in a negative 1/2, so I'm going back to this one, negative 1/2, negative 1/2 cubed is going to be negative. The middle term is going to be positive, and negative 1/2 minus 4 stays negative. So I get a positive. So far I'm positive, positive, negative. And then 5, let's see, 5 cubed is positive, 5 plus 1 squared, positive, 5 minus 4, positive, so I get a positive value. So my 4 intervals give me intervals that go increasing, increasing, decreasing, and then increasing again. So we know from the first derivative test that if we're increasing and continue to increase, nothing happens. If we go from increasing to decreasing, we have a max, and from decreasing to increasing, we have a min. So what do we have here? We have to have a max at 0, and we have to have a min at 4. So the two answers are 2 and 6. 13. Find the equation of the line tangent to the graph of y equals x minus 2 to the 4th times x minus 1 squared at x equals 3. So if I'm finding the equation of a tangent line, I need a slope and I need a point. Well, I have the x value of the point. I just need its y value, so I'm going to take the 3 I'm going to plug in 3 to my function. 3 minus 2 is 1. 1 to the 4th is 1. 3 minus 1 is 2. 2 squared is 4. 4 times 1 is 4. So I've got a point. And now I need to find the slope. Well, the slope is going to be when I plug in the derivative of y, which is going to be, we're going to use the product rule. So it's going to be 4 times x minus 2 cubed times x minus 1 squared plus x minus 2 to the 4th times 2 times x minus 1, which gives me 4 times x minus 2 cubed times x minus 1 squared plus 2 times x minus 1 times x minus 2 to the 4th. I'm not going to worry about simplifying that because all I care about is taking this and plugging in a 3. So if I plug in a 3, I get 4 times, that's going to turn into 1. And then 3 minus 1 is 2. 2 squared is 4. Plus 2 times 2 times 1. So I get 16 plus 4 gives me m equals 20. So my slope is 20. I've got a point. I'm going to use point slope form. Y minus 4 is equal to 20 times x minus 3. Simplify that a little bit. Y equals 20x minus 56 is the equation of my line. 14, same thing. Find the equation of the line to the graph at x equals 6. So once again, I'm going to take my ordered pair, find my ordered pair. I'm going to plug the negative 6 in for my x's, and I'm going to get 4 for my output. And then once again, I need to take the derivative. So y prime is equal to 3 times x plus 5 squared times x plus 2 plus x plus 5 cubed times 1, product rule once again. And I'm going to plug in a negative 6, so it's 3 times negative 6 plus 5 is negative 1. I square that, I get 1. And negative 6 plus 2 is negative 4. Plus negative 6 plus 5 is negative 1 cubed, which is negative 1 times the other one. And I get negative 12 negative 12 minus 1, which gives me a slope of negative 13. Apply my point slope form. Y minus 4 is equal to negative 13 times x plus 6, because it's x minus x1. And once again, I rearrange. Y equals negative 13 x, and then negative 13 times 6 is negative, what's that going to be? Negative 60, negative 78. Negative 78 plus 4 is negative 74. Alright, and then number 15, the volume of a sphere of radius r is v equals 4/3 pi r cubed. If the radius increases at a rate of 2 centimeters per second, at what rate is the volume increasing when the radius is 5 centimeters? So I read this, I see these words rate all over the place. I'm thinking related rates, which means I need to have something in terms of d over dt. I'm taking a derivative with respect to time. So if the radius increases at a rate of 2 centimeters per second, that's going to be dr dt, which is 2. And it says, what is the rate that the volume increases? So that means I'm looking for dv dt. Well, so I'm going to take my volume formula, and I'm going to take its derivative with respect to time. That formula then leaves me with dv over dt. I'm using implicit differentiation. times, it's going to be 4 pi r squared dr dt. Plug some stuff in. dv dt is equal to 4 pi r is 5 times dr dt, which was 2, which leaves me with 200 pi. So my final answer, the rate of change of the volume over time, is 200 pi centimeters cubed per second. Part 2. If the volume increases at a rate of 600 cubic inches per minute, at what rate is the radius increasing when the diameter is 20? So this time we're given dv dt is 600. We're looking for dr dt, and we know that r has to be 10 because the diameter is 20. So it's going to be the exact same formula. dv dt equals 4 pi r squared dr dt. Plug in what we know. 600 is equal to 4 pi times 10 squared times dr dt. And that's going to leave me with 600 equals 400 pi dr dt. So dr dt is equal to 600 over 400 pi, which reduces down to 3 over 2 pi. So my final answer is 3 over 2 pi inches per minute is the rate of change in my radius. 16 through 22, we're going to use this graph. For what x values does p have a relative max? It's important to make sure we read this because the graph here is not p. This is the derivative of p. So for what value does p have a maximum? Well, p is going to have a maximum when the derivative changes from increasing to decreasing. So if we look, we have positive slopes on everything less than -2. These are all positive. And then between -2 and 0, we have negative slopes because we are below the x-axis. And then from 0 to 2, we're back to positive slopes. And then again from 2 to anything beyond 2, we're positive again. It just happens that at 2 itself, we're not positive or negative or 0. So for what value does p have a relative max? Well, it has a relative max wherever the slope changes from positive to negative. So that's going to happen at 2. So maximum at x equals -2. 17, for what values does p have a relative minimum? Well, the minimum is going to occur when it goes from negative to positive. It switches from negative to positive right here. So it has a minimum at x equals 0. 18, for what values does p have a point of inflection? So now point of inflection is the second derivative, which is the derivative of the derivative. And we know that points of inflection and critical values both occur when the given derivative is 0. So we're looking for the changes in direction. So if we have the graph of the derivative already, we're looking for the maximum and minimum values of that graph. So we have a minimum here, a max at 1, and a min at 2. So p has a point of inflection at x equals -1, 1, and 2. 20 on 1 intervals is p decreasing. So it's decreasing, we already talked about it, in this interval right here, because it's less, the derivative is negative. So it's decreasing from -2 to 0. Oops, apologize, misread that. 20 was decreasing, that was -2 to 0. 19 was increasing. Well, it's increasing wherever the derivative is positive. It's positive from negative infinity to negative 2. It's again positive here from 0 to 2. And then it's positive one more time from 2 to infinity. On what interval is p concave up? Well, p is going to be concave up when the derivative is increasing. So we already know that we change concavity at -1, 1, and 2. So we just need to decide what's the derivative doing, what's the graph of the derivative already doing at each of those 3 points. Well, for everything less than -1, we have negative slopes. The negative slopes of the tangent line for this. So we are decreasing, or concave down, at anything less than -2. I'm sorry, less than -1. Then we have positive slopes from -1 until +1, negative slopes from +1 to 2, and then positive slopes again when we are greater than 2. So where is p concave up? Is concave up from -1 to 1 and from 2 to infinity, and it's going to be concave down from -infinity to -1 and 1 to 2. Alright, last page, number 23, given that f is defined as -x squared plus 18x minus 78, and it has a relative extrema at 9, choose all correct statements. Well, it'd be nice if we could figure out if that extrema was a max or a min. So let's see how we got that. So f prime of x is going to be -2x plus 18. Set that equal to 0. So x is definitely equal to 9 is my is my critical value. I can make my chart. There's my 9. If I plug in 8 and a 10, if I plug 8 into my derivative, 8 is going to be -16 plus 18, that's 2, so that's positive. And if I plug in a 10, I get -20 plus 18 is -2, so that's negative. So f is negative in the interval -infinity to 9. Nope, that's not true. It's negative from 9 to positive infinity, so that's option 2. F prime is positive in the interval all real numbers. That's not true. Option 4, f prime is positive in the interval 9 to infinity. Nope, it's negative. We already decided that. And f double prime is positive in the interval -infinity to infinity, or f double prime is negative in the interval -infinity to infinity. Well, let's go ahead and check. What is my second derivative? That's just going to be -2. Well, if my second derivative is negative, that means that f prime will always be negative because there's no place to plug it in. So we have 6 as well. 24, the graph below shows the velocity of an object as a function of time over the interval 0 to 6. At what time is the object furthest to the right? So it's furthest to the right at 2.5 seconds. And how do we know that it's furthest to the right at 2.5 seconds? Because we have positive velocities, and then right here the velocity becomes 0 and then becomes a negative velocity. Well, we know that velocity is a speed and a direction. So if we have positive velocity, it means we're moving one way, and if we have a negative velocity, it means we're now moving the other way. So if we change directions, that's the furthest out that we ever got, which happens to be at 2.5 seconds. Number 25, at what time does the object change direction? Well, that's the same question, 2.5 seconds. At what time does the object reach its maximum speed? So this is important that it was speed, not velocity. Speed does not care about direction. So we're looking at maximum speed, so we're looking at the velocity without the sign. So the greatest speed in the positive direction was 2, and then we go to the other side and it looks like our greatest speed is 4, so that occurs at 6 seconds. 27. On what interval is speed increasing? Well, speed is increasing between 0 and 1 second. Once again, this is speed, not velocity, so we're just looking for where is the slope getting bigger in the positive direction or more negative in the negative direction. So from 0 to 1, the slope is increasing. From 1 to 2, it's not doing anything. From 2 to 2.5, it's decreasing to 0, and then it starts to increase in the negative direction, so we're speeding up again. So that's 2.5 to 3 seconds, because at 3 seconds then it stops again, and then it increases again from 5 to 6. And then what is the object's acceleration at 2.5 seconds? So remember, the acceleration is the slope or the derivative of a velocity graph. So if we already have a velocity graph, we have to look for what is the slope of the graph at 2.5 seconds. Well, here's 2.5 seconds. This happens to be a line. So if we take the two endpoints of the line, that point right there is at 2, 2. This point here is at 3, negative 2. And then if I apply what we know about slope back from algebra 1, y2 minus y1 over x2 minus x1, that's negative 4 over 1. So we have a slope of negative 4, which means my acceleration is, let's see, did we have units? No, it's just going to be units per second squared. Alright, and then number 29, a differentiable function has the values shown in the table. So we have x is 0, 1, 1.5, 3, and 4. F of x is 4, 3, 2, 1.5, and 1. Estimate f prime of 1.5. So remember, f prime, derivative. Derivative is the slope of tangent line or instantaneous rate of change. So I want to know what's happening at 1.25. Well, 1.25 is right in between those, so we can get close to that by finding the average slope between those 2 points. That's probably the best. That's going to be the best way to estimate it. So all we need to do is take so f prime of 1.5 is equivalent to the slope of f between, I'm sorry, let me try that again. So the derivative of f at 1.25 is going to be estimated appropriately by finding the slope of f between 1 and 1.5, because 1.25 is right in between them. So I'm going to take f of 1.5 minus f of 1 over 1.5 minus 1. That's just my slope of a secant line. So f of 1.5 is 2, minus f of 1 is 3, over 1.5 minus 1. That gives me negative 1 over 0.5. Negative 1 over 1/2 is negative 2. So my estimate of the slope of the function at 1.25 is found by finding the slope of the secant line between 1 and 1.5, and that gives a slope of negative 2. Alright, and then the last question, number 30. Function g is continuous on the interval shown on the table above. Using a trapezoidal approximation with 3 equal subintervals, Euro finds that the integral from 0 to 9 of g of x dx is equal to 72. What is the value of unknown c? So we've got the trapezoidal approximation. I'm going to start by making a sketch. So here's g of x, here's x, and I know that at 0, I'm up here at 10. At 3, I'm at 8. At 0, 10, 3, 8. At 6, I'm at C. I don't know where C is. I'm just going to kind of guess. That's what we have to find. We have to find C. And then 7, 8, 9. I'm back at 8. So I have 9, 8. So I've got some kind of a weird function that does that. And I'm looking for the integral, or the area under this, from 0 to 9. So what we're going to do, what it tells us to do, is use the trapezoidal approximation to figure out what the area is. So a trapezoid is going to look like that. And we're going to have a whole bunch of little trapezoids. Not a whole bunch, we're going to have 3 of them. And we're going to calculate the area of each of those trapezoids. We know that the area of a trapezoid is 1/2 the height times base 1 plus base 2. So if we turn it on its side, these are my base 1 and my base 2, and this is the height. Well, the good news is the height's always the same because it wanted 3 equal intervals. So each of those intervals is 0 to 3, 3 to 6, 6 to 9. So each interval is 3. So each trapezoid has a height of 3. And then the bases are the lengths of the y values. So all I need to do is find the area of each of those trapezoids and add them together. So my first one, I've got, well, so first of all, let's start with 1/2 h. That's going to be the same for all of them because the h is 3. So it's really just, in this case, it's 3/2 times b1 plus b2 because the h was 3. 3 times 1/2 is 3/2. So all I have to do now is I have 3/2 times base 1 for this first trapezoid is this length, which is 10, plus base 2, which is this length, which is 8, plus, now I have my second trapezoid, which is 3/2 times base 1, which is now 8, plus base 2, which is C, plus 3/2 times base 1, which is C now, plus base 2, which is 8. And then we're going to simplify this as much as possible. Well, so we know that the area is 72. So there's my function. I'm going to clean this up a little bit. I see that I have a 3/2 in everything. And then I'm left with 10 plus 8 plus 8 plus C plus C plus 8 equals 72. Simplify a little bit more. 3/2 times, let's see, 10 plus 8 plus 8. That's 34 plus 2C equals 72. So 34 plus 2C is equal to 72 times 2/3, because I'm going to do the reciprocal. That gives me 48. So 2C is equal to 48 minus the 34. That's going to be 14. So C has to be 7. So we found the missing value of C. And that's going to be it for the non-calculator review for the final exam.